All right, let's talk about constant acceleration in 1D kinematics. We've looked at constant velocity. I now want to extend our kinematics to include when we have constant acceleration. You know about acceleration. Think about when you are in your car and you're coming to or leaving a stop sign. As you approach the stop sign, hopefully, you are slowing down. That would be a negative acceleration. As you leave the stop sign, you would be speeding up. That would be a positive acceleration. Words like speeding up and slowing down are words we can use to describe acceleration. Note that these are different from fast or slow. We use fast and slow to describe velocity. We'll use words like speeding up or slowing down to describe acceleration. That means acceleration is different from velocity. Most physics students have a real difficulty in explaining the difference between acceleration and velocity. Remember that the rate of change of displacement is velocity. We can extend this one more time and see how the rate of the velocity changes. We call the rate change of velocity acceleration. Formally, here's the mathematical expression. Acceleration is going to be delta v over delta t, or v final minus v initial over time. Look at that equation again. It looks kind of like a slope, just like the delta x over delta t was. Now, we'll see that there's going to be similarities between the two. This is, again, the formal definition. Acceleration is v final minus v initial divided by t. We usually let the initial time be 0, so the t final simply becomes t. Again, look how similar this expression is for that of velocity. We typically do not differentiate between a vector acceleration and a scalar acceleration. Acceleration is always a vector, so it'll always have a direction associated with it. Remember, in 1D kinematics, plus signs represent positive motion, negative signs indicate negative motion. Those are the directions. In 2D, we're going to need a little bit more math. We will also never worry about a change in acceleration. Our accelerations are going to be constant or 0, which is still a constant. So that means there will be no difference between an average acceleration and an instantaneous acceleration. We'll just call it acceleration. So we can extend our graphical understanding to include acceleration. Just as the slope of an x versus t graph is velocity, then the slope of a v versus t graph is acceleration. It's going to be that direct. The official units for acceleration will be meters per second, which we better represent by meters per second squared. Look at this little kind of graphical representation I have. If you start with an x versus t graph, you take the slope of it, you get velocity. Now that you have a velocity versus time graph, if you take the slope of it, you get acceleration. We'll talk more about the graphical relationships between all of these in another video. This brings us to the 4 kinematic equations we will use for all our kinematic needs. There are no more equations. People really get upset when they think they have to memorize all these special equations. Well, you really don't. In my class, I will give you the equations, and there's only 4 of them anyway, so it's not that big of a deal. Here's the first one. X final equals x initial plus v initial t plus 1/2 a t squared. This relates an initial position to an initial velocity, an acceleration, and time, and it tells you where you will be located at some future time. Here's the second equation. The second equation does not have acceleration in it, but it does have your initial and your final velocity. X final is equal to x initial plus 1/2 v initial plus v final, all of that times t. You're effectively finding an average velocity, that's the 1/2 v initial plus v final, over time to give you your final position. So if you don't have acceleration, you would use this equation. Third equation, v final equals v initial plus at. This allows you to find the initial or the final velocity given the other variables. It shows that velocity is going to be a linear relationship with respect to acceleration and time. And then the fourth equation, this does not have time in it at all. The time parameter has been removed. V final squared equals V initial squared plus 2a times the quantity x final minus x initial. So this would be the equation you would use if you did not have any time as one of your knowns. Pay attention to the subscripts. Make sure you know what they mean. The F stands for a final position or location. The I stands for the initial the initial situation. Pay attention to the symbols also. X means displacement, and we measure that in meters. V is a velocity measured in meters per second. A is an acceleration measured in meters per second squared, and then T would be measured in seconds. This will be important in the future because when we have problems involving kinematics, you'll be given a bunch of words in a problem. You will have to match those words and those values to various things in the equations. Then you'll pick which one of the equations will best represent or allow you to solve what you need. This is it. These are the only 4 equations that we'll need. There's nothing else in it. These are the only ones you have. Look at the equations again. If you're moving with a constant velocity, that means we're not speeding up or slowing down, and so the constant velocity means the acceleration is 0 meters per second squared. Equation 1 would reduce down to a constant velocity linear equation. Equation 2 reduces down to the same, since V initial equals V final, and equation 3 and 4 also show that V initial equals V final. Otherwise, we will have an x versus t equation that is quadratic in time. Remember in your math, this is the equation of a parabola. At worst, in the worst cases, the most complicated x versus t graphs will be a parabola. We also will then have a v versus t equation that is linear in time. At worst, in the worst case, the most complicated v versus t time will be a positively or negatively sloped line. If the velocity is constant, meaning that the acceleration is 0, v versus t is still a line, but now it's a flat line. To review, x is a variable that represents distance or displacement. We describe it with words like where or how far, and we measure it in meters. V will be a variable that represents speed or velocity. We describe it with words like fast or slow. It measures the rate change or the rate that displacement changes, so the SI units will be meters per second. One more time, we have acceleration being a variable that represents, or A is a variable that represents acceleration. We'll describe it with words like speeding up or slowing down. It measures the rate that velocity changes, which means that the SI unit will be meters per second or meters per second squared. Finally, there's one variable that ties them all together. This will be time. Time will be the independent variable, and we will measure that in units of seconds. T, or time, we can describe with words like when. Let's look at an example of a graph with a constant acceleration. Remembering what equation 1 was, it's going to be a parabola. In this case, I'm going to show you the acceleration is going to be a positive value, so the parabola should open up. Here's the graph. It looks like we start at 0 and we are speeding up. So as time goes on, we are covering further and further distances in each unit of time. It's not a line. This looks like a curve, and it does look like a parabola. In this particular graph, as I mentioned, we started with initial velocity of 0, so we started at rest, and we started at the origin. Here's another graph. Positive acceleration, but starting at a non-zero initial velocity and a non-zero initial position. These are just the x sub i's and v sub i's that we put in the equations. It's still a parabola. It still looks parabolic, just shifted up and to the right. So here's my graph. Looks very similar to what we saw before. Again, it's a parabolic shape. One thing to notice then is that if any x versus t graph has a curviness to it, looks like a parabola, it means the acceleration is not 0. If the acceleration were 0, this wouldn't be a curvy graph, it would be a linear graph. One of the neat things about kinematics is with a little practice, you should be able to look at a graph. If you see curviness in an x versus t, you know that the acceleration is not 0. If it is not curvy, if it's just linear, well then you have a 0 acceleration. Here's another example. Object will start at rest, but it's going to be located some distance away from the origin. It's going to have a negative acceleration. That means it's moving backwards. It will be moving backwards towards the origin, but speeding up in the negative direction. This can be a little bit confusing. Speeding up seems to be positive, but backwards is negative, so a positive times a negative is a negative. In this case, my object is going to have a negative acceleration. It'll be moving backwards from the positive side. So here's the graph. I started at about 75 meters. It looks like I'm moving backwards towards the origin, but as each moment of time goes on, I seem to be moving backwards faster. Again, note the parabolic shape. Any curviness in the x versus t graph will accelerate or indicate a non-zero acceleration. In this case, it's going to curve downwards. Here's another example of an object that has a positive initial velocity, but a negative acceleration. This means my object is still moving forward, but it's slowing down. Look at the numbers again. Moving forward seems to be positive, but slowing down seems to indicate negative. Positive times negative is negative, so this is also going to be a negative acceleration. This might be a description of you approaching a stop sign. So, I'm moving in the positive direction, but each time I seem to be moving less and less distance in the positive x direction. It's still curvy, it's still a parabola. That means I have a non-zero acceleration, but now this graph is opening to the right rather than opening. That's it for constant acceleration kinematics. You need to practice. Practice makes perfect. We'll do a bunch of problems and worksheets in class to make sure we can go through these problems and do them right. When you're given a problem, I think the best way is to write down what you know, completely with the units. Write down what you're trying to find out. With that little chart in front of you, you should be able to pick one of the four kinematics to solve for the unknown. You should be able to read between the lines in the problems. If they tell you a number is meters per second, you know that's a velocity. If they tell you a number is in meters, you know that's an x. If they tell you a number is meters per second squared, you know that's an acceleration. Problems can sometimes seem way more complicated than they are, and sometimes they have multiple parts to them. Sometimes you may even have more than one object that's moving. If you treat each little part separately, do the kinematic physics right there at that particular time, you'll find that the problems aren't all that hard. Slow, logical, methodical approaches will allow you to master these types of problems.